Good morning, everybody. Today we are going to start chapter 4 in our textbook, and this will be lecture number 19. So this is where we begin chapter 4. We will cover chapter 4 in 3 lectures, and then we will take a moment, a pause to review for our midterm exam, which will be a week, well, 1, 2, 3, 4 lectures, 3 lectures, 1 review, and then the midterm. So, and we'll take a whole day next Monday, a week from today, to go over the material for the midterm exams. So, so that you'll be prepared. All right. So today, chapter 4 talks about a concept of pure bending. And this is a very limited or very specific geometry that we're going to talk about today. Just like when we were talking about power transmission shafts, we limited our discussion only to circular or hollow circular shafts. Today we're going to limit to one particular type of a configuration. And one way or one example of this limited configuration is if we have a set of free weights and a person lifts the free weights so that there's a force up and a force down in equal and opposite directions, and that the bar of the free weights is bent in such a way that a moment, or the moment of a couple, if you call that term, bends the bar without any shearing stress. So in pure bending, we only have normal stress. Now, I will contrast this with general bending, which we're not going to do any analysis for today. We will later on. But in general bending, we have a case like a wall with a signpost extruded from the wall. And in this case, the difference is, if you look at the way that the signpost is bent in this more general case, the circular surfaces are not concentric, and the end of the structural member remains straight, whereas in the pure bending, the end remains curved like this. So the difference between this and the more general case of bending is that we have a situation with general bending where, if we think about the structure as having lamina, that these laminae are being pulled differentially from each other. So if you think about this as being little layers, this is a gross exaggeration of the geometry, but this layer is pulling against this layer, and this layer is pulling against this here, and that creates a shearing stress. Whereas in pure bending, the layers are not pulling against each other. They are just stretching different amounts. So that on the top layer, we have the longest curve, and down here, we have the shortest curve, and somewhere in the middle, we just have the original length. But nothing is really shearing against anything else, and so this type of a configuration results in no shearing stress, but we definitely have a normal stress. Okay? So the reason that we look at pure bending is so that we can analyze this idea of what happens when we bend an object without complicating it with this shearing component. And then we'll learn this part, and then in a later chapter, we'll extrapolate our conversation to the more general case of normal stress and shearing stress from bending. All right, so pure bending, once again, which is the topic of chapter 4, occurs where tau is equal to 0, but sigma has some value. Now, what we do, first of all, to break down the geometry of this situation is we look at anything that's bent in basically a way that the ends of the structure will, if we extrapolate the angle between them, that they will focus on some center point, which we just call C. And the distance from the point that remains unbent to that point C is called rho, which is called the radius of curvature. This is where I become so aware of being left-handed. There we go. All right. So basically, as I had said before, there is this relationship with where we basically have the lamina of a structural member in pure bending can be conceptualized as arcs of concentric circles. Right? Now, it turns out that the place where the structural member in pure bending is neither elongated nor shortened is referred to as the neutral axis. And the neutral axis occurs rho distance from the center of curvature C. Now, any distance that we are from the neutral axis to a lamina in the same direction along rho is referred to as y. So above the neutral axis, the distance from C to any distance above the neutral axis is referred to as rho plus y. And below the neutral axis, it is referred to as rho minus y. Okay? So all we're really doing here is establishing the geometric relationship. Now, if we refer to the angle that is subtended by the extension of the ends of our structural member to the center of curvature, if we refer to that as theta, we can then see that here on the neutral axis, the length of this arc, L, is equal to rho times theta, as long as theta is measured in radians. And we can further say that if we call the altered length either above or below the neutral axis as L prime, we can say below that L prime is equal to the quantity rho minus y times theta. And above, we could say L prime equals rho plus y times theta. Okay? And if we then consider that on any lamina, the change in length, in other words, L prime, is going to be L plus or minus del. We can say that del then is equal to L prime minus L. And that would actually be, if this is actually written for above the neutral axis. However, you can see that if del is negative, it would just place it below the neutral axis. So we're sort of saying del is positive means above the neutral axis or away from, and del negative is below, the way I have this drawn. But really what I'm talking about is away from the center of curvature. Okay, so if it was curved upward, this would be the opposite. But if we just use this nomenclature then, we can then say that del is equal to L prime, which is, let me continue this on another page here. Therefore, del is equal to L prime, which is rho minus y times theta, minus L, which is just rho times theta. And if you just continue this through, we get rho theta minus y theta minus rho theta. You can see that those go away. And I'm told then that del is equal to minus y times theta. So that basically is saying below, which is negative, del is negative, above, it's a positive. Okay. We also further know that in general, for normal stress, epsilon, or the strain, is equal to del over L. And so in this case, if we substitute this in, we get minus y over theta times L, which we know is rho over theta. And what we get then is we get rid of that angle theta, which is a real pesky kind of a thing to measure. I mean, because these bends are so small, theta tends to be it tends to be a difficult property to measure. So we really are not interested in measuring it. We're more interested in finding some things that we can measure and some things that are pertinent to the geometry, not of the center of curvature, but of the structural member itself. And so we get then that epsilon, and since we're talking about in the x, well, they call it x direction, then is equal to minus y over rho, which basically tells us that the strain on each lamina is positive above the neutral axis, is negative below the neutral axis, and further is proportional. When I say proportional, I should clarify linearly proportional from the top to the bottom of the structural member, and it is also, the strain is equal to 0 at the neutral axis. Okay. So what I mean by this is, let's just take a look at our original structural member, and let's just say that it started out being rectangular. Now I know that is unrealistic for the example that I gave, which is a free weight, the bar lift with free weights. But if we turn this on, if we subjected this to a couple, another example would this be, perhaps there's a rigid end cap here and here, and we put a C-clamp on both of these, and then we pull down or up. Okay, but in this case, we pull down to look like that. What this tells us is that if we take a cross-section of this bar, so this is my bent lateral, if my cross-section looked like this, the first thing is it would thin out a little bit on top, and it would thicken up a little bit on the bottom, right? That's according to Poisson's ratio. But basically, if I looked at the strain, my greatest elongation would take place here, my greatest contraction would take place here, and at the neutral axis, wherever that might land, the strain would be equal to 0. So a graph of my strain looks like this on the cross-section. So we have the maximum elongation here, no elongation or contraction on the neutral axis, and the maximum contraction on the bottom at the edge, and that it's a linear proportion across that section. Okay. Now, on the next page, they do a weird little jump, and I don't really like it, but I'm going to put it up here so that you have it. They start referring to C a little bit differently. And we've been using a capital C as the position of the center of curvature. So let's do this. Capital C equals position of the center of curvature. And on page 244, your authors begin to refer to small c as the distance from the neutral axis. So we've called that in the past, we've called that y or negative y. So not real keen on this idea. But basically then, using that nomenclature, we can see that the epsilon, or the strain in the x direction, is equal to c over rho, or we can say that epsilon x is equal to minus y over c times epsilon max. Okay. Now, it's very important to notice, as in all of our prior discussions, this is only applicable in the elastic range. So in other words, once we exceed the elastic limit, where we have sigma epsilon, just like any other graph, once we exceed this elastic limit, none of these equations are applicable, because then we take on a permanent deformation. So just like with everything else in this class so far, we've focused our discussion on staying within the elastic limit. All right. So let's take a look at some useful equations. The first thing is that from an engineering point of view, locating that center of curvature, or theta, the angle that is subtended, are not practical things to do. So what we really want to do is to limit our discussion as much as possible. We'll do some stuff with the center of curvature and so forth, but basically want to limit ourselves to a discussion of what's going on this structural member. What can be measured on the structural member itself, okay? Now there's one other picture before I get into this that I want to point out to you. If you look at the top of page 243, there is a misleading picture. It is not incorrect. It is explained, but it's misleading. Now, like I said before, if we have a structural member that was originally straight and we bend it downward like that, the top part of this is going to contract, and the bottom part is going to expand, right? This is correct and not misleading. But on page 243, your authors draw an upwardly bent structural member like this. And then they draw a cross-section that looks like this. This is the part that is misleading. Because if you were to do that, when this contracts, the cross-section of this would actually be a trapezoid in this shape, wouldn't it? Because if this contracts, it's going to expand on the axis. That's what Poisson's ratio tells us. And here, if this expands, it's going to contract, on the cross-section. If the lateral face, if the axis contracts, the cross-section will expand. If the axis expands, the cross-section will contract. So this is correct, but this fits this type of a bending configuration, and your authors draw this bending configuration next to this cross-section. So these two are both correct in terms of our analysis, but they don't go together. Okay? So just so that you are aware of that. And they do explain that in the text, but when you just look at the picture, it can be somewhat misleading. So I want to alert you to that. All right. Now, in general, I'm not going to go through the derivation of this, but the derivation to compute sigma for pure bending is shown on pages 244 and 245. But the basic equation, first of all, let's look at this, and let me just ask you a question. Above the neutral axis, do you think this is going to be in tension or in compression? The way I have it drawn. If we're bending downward, this is elongating. Yeah. Tension. Very, very good. And down here? Compression. Right. And here, on the neutral axis, it's a neutral, right? That's actually, I mean, we've worked it from a geometric point of view, but we call the neutral axis neutral because the stress at the neutral axis is equal to 0. Okay? So, so very good. Sigma then, if you see, if we have a positive y, sigma is going to be positive because we're in tension. Below the neutral axis, it's going to be negative. And if this is symmetrical, the amount of compression on the bottom and the amount of tension on the top will be the same, only if the cross-section is the same. But basically, the sigma, then, in the x direction along the axis is going to be equal to the negative of a moment, which we'll describe in just a moment, times y, the distance from the neutral axis, over I, which is the moment of inertia of the cross-section. And I'll explain this. M is equal to the applied moment y is equal to the distance from the neutral axis, and I is referred to as the moment of inertia of the cross-section. I will explain all of this too, but I need to write it out first, about the neutral axis. All right. Now, there's also, if we look at sigma max, if you look at this, sigma max is going to occur at the top and at the bottom. And sigma max then is going to be the moment times that little c, which I said misleadingly to me, is the maximum distance from the neutral axis over the same I. Right? So, a moment, let's talk about each of these. We can describe, we know what sigma is. It's going to be in dimensions of force per area. We know what y is, the distance above or below the neutral axis. And so we really need to spend some time talking about what is a moment and what is a moment of inertia. Okay? So that's what we're going to do for about the next 10 minutes. A moment is a force acting through a distance. And for pure bending, that tends to be the moment of a couple. So once again, let's think about our free weight example again. If you have a weightlifter who is pushing up with his hands at 2 points on that bar, and the weights that are pulling down, and if he is symmetric, he or she is symmetrical, you can see that this will tend, this couple, this is referred to as a couple, write that down as a tangent, is equal and opposite parallel forces. So we'll talk a little bit more about that as well. But this, the moment of this couple tends to rotate it this way. The moment of this couple tends to rotate it this way. And if everything is symmetrical, the weights are symmetric, the hand placement is symmetric, the amount of rotation clockwise and counterclockwise will be equal to each other. So that the bar doesn't go anywhere, there's no translation, there's no net force. The sum of the forces is zero, but there is still this tendency to rotate here, this tendency to rotate here, which are offset by each other, so the tendency then is to bend rather than to go into a rotation. Moment of inertia. Let's see, I want to talk about something else here before I continue this. A moment then, because it is a force acting through a distance, has dimensions of force times length. So a moment has the same dimensions as torque. In other words, foot-pounds, Newton meters, etc.
Moment.
Yes, it is. Torque and moment are the same. They're just at different planes. So when we're looking at something twisting, we talk about a torque. When we're looking at something bending, we talk about a moment. But you're absolutely right. It's physically pretty much identical concept. Just depends on the plane that we're looking at. Yeah. So that's a very good observation. All right. What is a moment of inertia? Well, there are two types of moments of inertia. One is referred to as a mass moment of inertia, and the other is an area or areal moment of inertia. I always just abbreviated MOI just for moment of inertia, just because I get tired of writing it over and over again. I'll write it once more. Okay. And it is the rotational equivalent of mass. So when I say that, what I mean is, let's look at Newton's second law. Force as a vector is equal to the scalar mass times acceleration. So what that means is, if you think about it, for a given force, acceleration is greater the less that mass is, right? Or for a given acceleration, the more massive a body is, the more force is required to accelerate it to that particular value. Or I would say mass opposes acceleration for a given force, right? All right, now the equivalent to this equation is that moment is equal to moment of inertia times alpha, which is angular acceleration. So what that means is that moment of inertia opposes not linear acceleration, but angular acceleration, which is related to the idea of rotation. So if we take something like this ruler, in the case of a pure bending moment, if I bend it like this, the resistance that I feel is an expression of the moment of inertia. I want to be really clear. Moment of inertia is primarily a mathematical concept, but this is one of the things that it describes, or that we can use to describe a physical property. Now, if I take this same ruler, same mass, same shape, and I try to bend it in this plane instead, in other words, I want it to bend so that this elongates and this stretches, is it going to take me more moment or less moment to bend it than if it's in this shape? More. That's it exactly. And it turns out that the height of an object, so here the height is the full inch, here the height is just this wee little bit, but the height is the dominant factor in determining the moment of inertia. So moment of inertia has an analogy to mass, but it's obviously not mass because this ruler has the same mass, but it bends very differently in this direction than it does in this direction. And to bring up the idea that Christian came up, the same sort of a moment, if we have those, if we try to twist it, this is a torque. So it's just the direction that determines whether it's a moment or a torque. So, excellent point. Yeah? Yes, that's fine. Well, let's leave it right here then. That'll be the end of the discussion. We have a moment of inertia of common geometric shapes in the back of your textbook, and we'll pick up there next time. So, you guys have a great day. There we go.